here the bits per minute participants, by these participants, and the number of words that they, or symbols that they can produce. So bits per minute here, it's for fixed number of sequences, 15. This is the bit per minute you get, and then you can optimize that, and by looking at how the accuracy evolves with the number of sequences for that particular subject, and you can optimize the number of sequences. And for participant 1, 8 sequences suffice here to get what was it again, 70% accuracy. Then you come to 5 bits per minute, and this one is the champion here with 12 bits per minute. And you need about 5 bits, as you know, to communicate one character. So this way you can communicate something like 1 character per minute or something like that. Now, if you support that with visual information, as we just have shown, that you combine that some visual information that you have a sort of, that the subject knows that, okay, this is now the beep corresponding to column 6, for example, then you see that the accuracy goes up, and also the bits per minute goes up. You can optimize it, and then you see that you indeed have achieved more than double the number in terms of bits per minute. So this is an auditory visual interface for a brain-computer interface based on event-related potentials. And then this is the next was a bit of there is this company that sells this equipment, GTEC. They sell EEG equipment with some software and whatever to do brain-computer interfacing, and they have been going to a lot of fairs where technology is shown at conferences, and they do collect there from a whole big number of subjects with their equipment, of course, and their software. They collect a lot of data, and this way they have been publishing a number of papers for the different paradigms. So for the P200 paradigm, they tested 111 subjects. They spelled a 5-character word after 5 minutes of training with copy spelling setting. And they used a simple LDA classifier, no feature selection, and 15 trials. So 15 rounds of identification. And then they saw that almost 73% of the subjects could spell with 100% accuracy those 5-character words, and with 15 averaging, of course, 15 times of averaging. But they also saw that 3% of the subject did not spell any character correctly. So these are the problematic subject, that we call them illiterate to that particular brain-computer interface paradigm, and you will see numbers for that. You do have individuals that are, for some reason, that paradigm doesn't work, and you can try another paradigm, and maybe that one does work. So there was a case here about these illiteracy. So this is the performance, 70%. You try to remember this number here, because for another paradigm, you will see other numbers here. For some paradigms, seemingly they work better than others. Okay, we have been discussing point 3, so next slide, event-related potentials. We can also look at another type of event-related potential, the so-called error-related potential, and that one occurs when a mistake is being made, and it has the potential to correct mistakes. Let's go through that. So next slide, so error-related event-related potential, it's a long word. And those are related to the subject perception of an error, the error that occurs. And this is presumably be generated particular brain area, and it can be picked up with your EEG electrodes over the frontal central regions of the scalp. And there was a difference actually between a subject error and an error made by the interface. If the subject is pretty sure that it was done selected correctly, and the machine, in this case the decoder, makes a mistake, then the shapes will be different. If the subject realizes that the subject made a mistake, or if the decoder makes a mistake, the shapes of the RFP will be different. And they will also be different and depending on the task that is being considered. You have a particular task, a particular paradigm, and it depends on the paradigm as well. So this is a pretty murky event. The error-related potential is pretty murky to work with because it depends on a lot of factors. And we did some research on that. And you will see that it is indeed the case that it's not that easy to work with. So we examined in case of the P300 mind speller, the typical speller as you know it. And we have been recording EEG responses to the feedback that appears on the screen. You select the character and then it appears on the screen what you have selected, and the response to that is being recorded. If this is the correct thing that you wanted to communicate, then the error-related potential should not be there. If it's a mistake, then it should be there, and you can pick it up. So we have been doing some work there. So the next slide shows 6 subjects, different ages. Well, it's more or less in the age groups you would expect for university research, let me put it this way. And yeah, different types of different typing sessions, different number of symbols being typed, and then you see the mistyping rate here. So we see the number of characters that were mistyped, and then on the bottom you see the plots. These are the grand average responses for all the subjects and so on, for the plotted against for individual channels. You see the green is the correct feedback, and the red is when the character is incorrect. And then you see indeed some differences, and you can take you can plot these differences here. Then you see a particular signature occurring around 400 something millisecond. There seems to be a peak here, but it also is channel dependent. And even, as I said before, it is also subject dependent. You see for particular electrode here, the frontal central electrode, you see these dependency on the subject, and then you plot it, for example, the difference here. You see a pretty you see a sort of pattern, a common pattern, but it really depends on the subject as well. So then you do some analysis, in this case, the coefficient of determination, R squared. So you try to figure out what is the fraction of the total variance explained by the class label. And of course, it should be as high as possible. You can have a threshold here. And you see that for individual subjects that the most significant ERP component is an early one. For subject 2, it's more in the region we would expect it. And you see that dependency popping up. And this is then on the right bottom plot, you see this is for all across all subjects. This is a particular pattern that you could use to extract your features to work around it. So next slide, you indeed see that there is something there, and there are ERP components there that can be used, but there is also a high variability, as you have seen, among trials because of the noise and that you always have in EEG. And then you have also that it really depends on the subjects. So there is quite some training needed on each individual subject to make it work. So you need to gather a lot of training data. It's not going to be easy. And remember, it's all one shot. You can't do any in practice. I mean, you can't repeat that error all the time, right? An error occurs only once, and you should be able to take a decision on a one-shot event. This makes it extremely hard. Okay, so you can try it. You can try to collect data, and how much. The question is then how much data do you need? How many examples of wrongly typed characters or wrongly decoded characters do you need? And the second point is, of course, is it really worth it? Remember, we had also alternatives like error correction, automatic error correction facilities, and so on. Is it really worth it? So we have been gathering data by using the backspace symbol, which we used as a cue for detecting the presence of an error-related